Okay, so it's recording my movements now and I can see them. Okay, so this is a consolidation of 6.1 to 6.3, and this is what I'm going to try to go through in class. There are more detailed versions of this on YouTube, but I think we can get through all this in one lesson. And so this is what I want to go through. I'm going to try to go through scale factors, dilations, and my exercise is going to illustrate the center of dilation concept, and then the algebraic descriptions. I'm going to try to do this all in this quadrant over here, and then I'm going to move over to this quadrant, and I might spill into this quadrant, talking about transformations which include dilations, and in that conversation we're going to talk about preserving distance and commutative property. Okay, so here we go. Try to do this all in less than a half hour. So without further ado, first say we have a point, and we'll say this is point D. Okay, and we have a point over here, we'll say it's point F. Okay, now I'm going to expand point F, these points, I'm going to dilate point F from point D by a factor of 2. Okay, so my scale factor in this case would be 2. Well, how would I do that? I could calculate the distance between here and here, right, using Pythagorean's theorem, right? Or I could simply just count the difference in blocks between my x value and my y value and double it both ways. Okay, so that's another way that I could do that, right? So I could just say, okay, my x value distance is 3. So my scale factor here, I'm going to double my scale factor. Okay, my distance from D to F is going to double. Okay, I'm going to dilate this distance by 2. Okay, my scale factor, in this case, my center of dilation is D. Okay, so this is my center of dilation. This is the reference point. So, you know, the definition of center of dilation is a reference point used to appropriately scale the dilation of a figure. Right, and the dilation for this one is my center point is D here. Okay, so anyway, you'll see what kind of all that comes together here when I compare the two over here. Okay, so anyway, so I'm going to go over 3. Okay, from here I got 1, 2, 3. I'm going to go over another 3. So I'm doubling it, right? I'm going to go 1, 2, 3. This is going to be where my f value is going to be. Okay, I'm ignoring my x-y axis here, right? Because your x-y axis is just a convenient like two-way ruler to help you count the values. Okay, and then from here to here, it's a change in 2, right? So it's going to be a change in 4 now. So it's going to be 1, 2, 3, 4. Now my f prime value is now 4. So my initial length from D to F was, this long, and my final length from D to F prime after the dilation is now this long. And if you wanted to go back, or if you were given these two lines, you could see, well, my initial y value was 4, my initial f value was 2. My final my initial f, so y, my initial up and down was 2, and my final f value is 4. So I could bend just like 4 divided by 2, and that would give me my scale factor. And then my change in x was from my initial point was 3, and then my final change in x was 6. So my final divided by initial is 6 divided by 3. Right, so your scale factors, if you can remember, my scale factor is any measure that I know any measure applicable to my after my dilation out of my before my dilation. Okay, so that could have been this line too, right? If I knew the distance of this line, and this would just be like the square root of 3 squared plus 2 squared, and this would be the square root of 6 squared plus 4 squared, but I'm not going to calculate that for the sake of time. Okay, now say I had a point. I have a point O. Okay, I had point O, right? And then I had a point D right here, right? And then I had a point F right here. Okay, let's make it point F let's make it point F right here. Point F is right here, and I'm going to apply a scale factor. That's not going to work. Let's make it right. Let's make it right here. Point F is right here. Okay, yeah, that'll work. Okay, so point F is right here. And let's apply a scale factor of, let's say 3 to 1. 3 to 1 from D to F. Okay, so my initial with my point of dilation, my center of dilation being O. Okay, all right. So my initial length from O to F, right? My initial length from O to F is 1, 2, 3. It's 3 over 1, 1, 2, 3. It's 3 over. Oh, sorry. 1, 2, 1, 2 over, and then it's 1, 1, 2, or it's 1, 2, 3, 4 up. Okay, but I'm pausing this for a second so I can figure out a way to explain this. All right, so the difference here is when we dilated this from this point origin, we simply went from here and we just added the 3 extra, right? Or we just went from here, we multiplied by 6, right? From here, we're from this point to this point, it's 1 over and 2 up. Okay, so we're multiplying this point, we have to multiply that by 3. Okay, so we're going to go from here, we're going to go 1, 2, 3. All right, that's going to be our third point up. Okay, and then we're going to go from this point, it's going to be 2 up, so we're going to multiply that by 2, it's going to be 6 up. So from this point, we're going to go 1, 2, 3, 4, 5, 6. So that's going to be our F prime. Our F prime. Okay, so we dilated this point. So this was our original line that we dilated, and it expanded this long, and it expanded this long. Okay, well, if you look at this, if you look at this one, it's pretty obvious. This line segment doubled in length. Okay, this line segment tripled in length. So that's what you should be expecting to see. So you'll note that when you take the first line segment, or the entire length of the line segment, divided by the initial length of the line segment, you will get the scale factor. And that's the relationship you'll see the entire time. You'll just have that gap from your origin. Okay, so where you count from just is different. Okay, now when you have like a built-in like ruler, if you will, you can use like reference points on that ruler and subtract and add from that if you don't want to count blocks. That's where you'll see the change in x minus the change in y and stuff like that. But that's all you're doing is counting blocks a fancy way. Okay, so that is how we figure out the scale factor and the difference in point of origin. Is they might have the point, you'll get used to the origin being the point of reference, and then you'll be using the points from that to figure out what the scale factor and stuff is. But just don't forget that this relationship is all that is. Okay, it's just counting x's and y's, the changes in x and the changes in y, and you don't even need the coordinate plane to do that. The coordinate plane is just a useful tool to help you identify the changes in x and the changes in y. Okay, so remember, in that scale factor is anything before anything about that dilation, that figure after, divided by anything before. That could be the length of a line segment. That could be the change in, that's like the number of y's before, after, divided by the number of y's before, or the number of x's after, divided by the number of x's before, right? So remember that stuff, okay? And then your algebraic expression for a dilation is simply your x comma y, and then your scale factor is represented by k times your x value, comma y, k times your y value. Right? That's all that is. Okay, so it just multiplies your k times your y value. And if you remember, if your k value or your scale factor is greater than 1, right, your object is getting bigger or grows. If its k is less than 1, it shrinks. It'll never be 0 or less than 0. Okay. Okay. So just remember that stuff. All right. So I'm a little ahead of time, a little ahead of the schedule here, so that's good. All right. So we talked about scale factors. We did a dilation from a point inside the dilation and center dilation and outside dilation, and we hopefully understand how that illustrates the center dilation concept. And then you talked about the algebraic description. Okay, now we're going to talk about transformations, which include dilations. Okay, so I'm just going to make up some image with this burgundy thing. I'm going to make I'll flip this around here. All right, so I have an image, and do like this here. This is my image. Okay, and I'll call this I'll do this. I don't know why I put it upside down. Okay, so this is A, B, C, and D. Okay, and we'll say that the first algebraic expression that I apply to this is will be x comma y yields, we'll do negative x comma y. So what is that? Think about it, pause it, think about it, maybe look it up in your notes. You should know by now, right? If the y value stays the same, but the x values swap, that is a reflection. Okay? So if you need to use an algebraic table, right, just do A, B, C, D, My x value is 7, negative 1. For b, my b values are 9, comma, negative 4. My d value is 5 and negative 5. And my 5, negative 5. And my c value was 7, negative 8. 7 and negative 8. Okay, so I'll shift over to like a blue, right? So my xy comparison is negative x, comma, y, right? So my new xy coordinates are going to be all these turn negative. It doesn't mean that they're turn negative because it's negative, but they're all positive, so they flip signs into negative. That's what that negative sign means. And then all the y's stay the same, right? So it's going to be negative 7, 9, 7, and 5, and all these stay the same. Negative 1, negative 4, negative 8, negative 5. Now I'm going to transpose all those. So my a is negative 7 and 1. That's a prime. Right, and my b is negative 9 and negative 4. That's b prime. My negative, so negative 7 and negative 8 is for my next one, is for c. Negative 7 and negative 8. Negative 7 and negative 8 is right here. Negative 8 is right here. Okay, so that is negative 7, that is c prime. Okay, and then d prime is negative 5 and negative 5. Negative 5 and negative 5. That is d prime. Okay, so my question to you is, wait a second, I don't think that was negative 7 and negative 7. Negative 7, let's check if I'm riding it over. Just misread it. Negative 7 and negative 7. That's c prime. Okay. That's supposed to be just single prime there. Okay, so I'm going to draw these lines. So my question to you is, were distances preserved? What does that mean? Well, that is asking you, were the distances between the vertices preserved? What does that mean? Well, were the distances between these points preserved? Between each point preserved? Well, did the distances between these points, A, B, C, and D, did they stay the same during this transformation? The answer is yes. They didn't stay the same because this was a rigid motion. What are my three types of rigid motions? A reflection, a rotation, and a transformation. Those are the three types of rigid motions. As long as the transformation is one of those three, distances are preserved. Okay, so this was a rigid motion and distances were therefore preserved. Okay, now let's go ahead. So I'm going to go ahead and do my xy coordinates over here, and they were negative 7 and negative 1, negative 9 and negative 4. I had negative 7 and negative 7 and negative 5 and negative 5. Okay, those are my xy coordinates. And now let's say that I apply a algebraic expression transformation of x comma y yields negative x, negative y. What is that? What is negative x, negative y? Well, let's take a look. My new xy coordinate would be the negative x, negative y of this one, right? So all the signs are going to change, but the x and the y's are going to stay the same, right? So this is going to be 7, 9, 7, and 5. This is going to be 1, 4, 7, and 5. So I'm going to go plot these. Okay, so this is going to be 7 and A is going to be 7 and 1. 7 and 1. That's A double prime. B is going to be 9 and 4. Wait, that's 7. That's 1 and 7. A is going to be 7 and 1. B is going to be 9 and 4. That's double prime. B is going to be 9 and 4. That's B double prime. Okay. Let's see. D is going to be 7 and 7. That's going to be D. That's C double prime. And D is going to be 5 and 5. D double prime. Okay. And if you can't figure out what that was a rotation of 180 degrees. Okay. All right. So now, what are we gonna? So were distances preserved during this? 7 and 7. Oh, that's 5 and 4. That's why that looked funny. 5 and 5. 7 and 7. What is A? 7 and 1. Okay. That looks better. Okay. And that's A. That is D. Alright, so there we go. Okay, that was 7 and 2. That dang line got me again every time. So this has been 7 and 2 the whole time. And this line fades over top of this, and it's 7 and 2, and it gets me every time. That's okay. I always notice it when I go to this side. So these are all 7 and 2. Alright, so that's A double prime. A double prime. Okay, there we go. So those are all 7 and 2, where it says 1 down here. These are all 7 and 2. But anyway, okay, so now I have this other one. Was distance preserved during this transformation? Yeah, it was. It was preserved. So now let's do an algebraic description of x comma y of, I can't do. Let's do 1/2 x comma 1/2 y. Okay, so this is a dilation about the origin. About origin. So origin's here. So that means for every one of these, we're going to take half of it. So half the distance. So of each one between the origin. Okay, so half of 5 is 2.5. Half of 5 is 2.5. So my new D location, this is going to be D fourth. Okay, and then A is going to be 1 and 3.5. This is going to be A to the 4th. Okay, B is going to be 4.5 and 2. So 4.5 and 2. That's going to be B. And then C is going to be 3.5 and 3.5. So 3.5 and 3.5. So right there. And all these will come together like this. All right, so my question is, was distance preserved? And the answer should be no. Distance was not preserved because it got smaller. Okay, and if I wanted to make sure and see if if my dilation was correct, I could go like this, line up all the vertices, and they should line up with the origin. That was C and D, or C and C and D, and then I got B here. It should be B, B. And then I have A. You can see that they all lined up with the origin there. Okay, and if I were to take like the distance from here, the distance from here, it would all be half. Distance from here, distance from here, they all be half. Or if I take the distance of this and the distance of this, it'd all be half. Or this distance, this change in x from C to D, and this change in x from C to D, it would be half. Right, this A to G is different, it's half, right? This is a change in 1, this is a change in 2, this is a change in 2, this is a change in 1, it's all half, right? It's all a scale factor of 1/2, right? So there you go. And then one more thing is the commutative property. So if I were to do this in a different order, would this be the same? Would it end up in the same result? Right, so if I were to do, say I started here, right, and then I did a 180 rotation, right, and then I reflected it across the x-axis, right, and then or was it the y? I reflected it across the y-axis, right, and then I dilated it. Would it end up there? Well, yeah. Yeah, it would, I think. So I did a 180 rotation, it would put it up here. And then I reflected it across the y-axis, it would end up here. And then I dilated it, it would still end up there. So it would be, the commutative property would exist here because it would end up in the same spot. Right? Say I ended up here, I did it here, and I mean that's really the only other way to do that. And then I dilated it first, and it would be small, right? And then I reflected it, and then I rotated it 180. It ended up there, right? Or say I reflected it, and then I dilated it, and then I rotated it 180. It would end up there, right? So, no matter what order I did this in, it would all end up in the same spot, right? And you could do that with patty paper. You could do that with the way I just did it, like in your mind, or you could do it algebraically with these right here. Right, and you could have done this algebraically too, up here on paper, right? You just put the table up here, and then instead of like doing your function up here would be 1/2 and 1/2, and you take these points like I have here, and it would be 7.5, right? And it would be 4.5 and 2. And it would be 4.5 and 4.5, and it would be 2.5 and 2.5, and that's where you see all these points anyway, right? This is actually 3.5 and 2, so it should be 3.5 and 1. That's where we made the mistake before. Okay, so that is right at 30 minutes, and I think I'm gonna do this in the classroom, and I think it'll help out for everybody. So I hope this works out, and that's lesson 6.1 through 6.3, and I hope you guys had a great day and understood all that.